So, good afternoon, everyone. Good morning also. So, we are now in stability. Stability is if a beam can be counted on to remain stable for up to the fully plastic condition, the nominal moment strength can be taken as the plastic moment capacity. That is M sub n is equal to M sub p. Otherwise, M sub n will be less than M sub p. Meaning stability is that when in element or a steel section is loaded, no, maabot siya sa iyahang inelastic range. Remember, we have the elastic, meaning the proportional limit, no, within the proportional limit, meaning the stress is proportional to strain, no. But beyond that, beyond the yielding point, no, beyond the proportional limit is your plastic condition or inelastic condition. So, kung stable ang beam, no, or ang section, meaning the nominal moment strength can be taken as the plastic moment capacity. Moabot siya sa plastic moment condition, no, if the beam or structure is stable. Otherwise, M sub n will be less than M sub p. Then otherwise, you have to use the M sub n. But if we try to like analyze a stable section, we have to use that nominal moment strength M sub n is equal to M sub p. Meaning we have to use the M sub p. As with a compression member, instability can be in an overall sense, or it can be local. Remember, in your topic of compression member, we have the different instability of column, no. It can be we have the global, no, instability, and we have also the local, no. Remember those itong topic sa midterm. Overall buckling. So for flexural structure or beam, the overall buckling is illustrated in figure A. When a beam bends, compression region above the neutral axis is analogous to a column, no? And in a manner similar to a column, it will buckle if the member is slender enough. So the same with column. So this beam here, no, in this figure, will also buckle if the member is slender, like the length to thickness ratio is dako siya, no. So meaning slender, depth to thickness ratio. So in here, kung taas rapid kayo ang beam or member, meaning it will buckle, no. Dili na siya stable. So we have this lateral torsion buckling of this beam, no. So if we try to look at some section, let me like a part of in here, no, kana siya. So unlike a column, however, the compression portion of the cross section is restrained by the tension portion, and the outward deflection, flexural buckling, is accompanied by twisting torsion. So say we will select the section of this beam. So actually this beam will experience lateral torsion buckling. So it will like change in position and will also rotate, no? This is the rotation. I mean, so the rotation, I mean, mo ispog siya dire, no? At the same time, mo rotate siya. So there is this lateral torsional buckling. If the beam is slender enough, no? Stability bracing, so to resist, no, this buckling, no, or to minimize this buckling, we have to brace the beam. So we have this lateral, LTB is the lateral torsional buckling. The lateral torsional buckling can be prevented by bracing the beam against twisting at sufficiently close intervals. Using either of the two types of stability bracing, we have the lateral bracing in figure B. Now, this prevents lateral translation. Should be applied as close to the compression flange as possible. So, to prevent lateral, meaning the movement side to side, no, sideways, you have to brace, no, duol siya sa flange. I-connect naman siya sa flange. Close to the compression flange as possible. Then, we have also torsional bracing in figure C, no? Kani siya. This one and this one. So, we have figure C prevents twist directly. It can be either nodal or continuous, and it can take the form of either cross frames or diaphragm. So there is this bracing, no, to prevent the torsional buckling. It can be cross frames, no, cross frames or diaphragms. So I think this one is steel gyapon. Then na ay steel plate diri gi-connect og bolt, or you can weld, no, diri nga portion to brace the beam. Sectional integrity. So whether the beam can sustain a moment large enough to bring it to the fully plastic condition also depends on whether the cross-sectional integrity is maintained. This integrity will be lost if one of the compression elements of the cross-section buckles. So this type of buckling can be either compression flange buckling. So ang imong flange is mo buckle siya, no? There is this local buckling at the flange. Or we have the buckling of the compression part of the web. So the web buckle, no? Local buckling gyapon sa flange ug sa web. So we have this sectional integrity. So either of this flange or web, no, buckle, or ang flange mo buckle or ang web mo buckle, either of that, there is the sectional integrity. So kuan gyapon siya, dili siya stable, no. Note, as discussed in chapter 4, compression members, whether either type of local buckling occurs, will depend on the width to thickness ratios of the compression elements of the cross section. So remember, the compression members, the local buckling depends on the width to thickness ratio of the compression elements. Effects of local and lateral torsional buckling. We have this 5 separate beams now represented on this load deflection curve. So there is this load versus the deflection, no, and the first yield is in this level, and the beam is simply supported now with uniform load. So this curves, no, is described by these effects of local and lateral torsional buckling. So the curve 1 is the load deflection curve of a beam that becomes unstable in a way that loses its load carrying capacity before first yield is attained. So at kining curve 1, wala pa siya kabot sa iyong first yield, ni unstable na siya. So meaning wala na tarong og establish ang section or ang beam, no? Wala pa siya ka abot. So meaning there is this lateral torsional buckling or naa siya'y compression flange buckling or web buckling, no? Local buckling siya. So, in curves 2 and 3 correspond to beams that can be loaded past first yield but not far enough for the formation of plastic hinge and the resulting plastic collapse. Actually, kaning curve 1, wala pa siya kabot sa first yield, no? Ni collapse na siya, meaning unstable na siya. So, the moment plastic, no, the M sub P is, you cannot apply the M sub P kaya wala man siya ni yield. Wala siya kaabot sa iyahang plastic limit. Nara siya sa iyahang elastic limit. Ni collapse na siya. No, so meaning wala na establish og tarong ang section or ang beam. No, meaning siguro wala siya lateral brace or wala siya bracing, no? Bracing sa lateral bracing or torsional bracing, no? Okay. Na-fail naman, no? Well, curves 2 and 3 correspond to the beams that can be loaded past first yield but not far enough for the formation of plastic hinge and the resulting plastic collapse. Yes, nakaabot siya first yield but yes, as stated now, but not far enough for the formation of plastic hinge, then the beam collapse, no? For curve 3, okay, that is curves 2 and 3, no? There is this elastic limit niya, proportional limit niya, then iabot sa point na maximum yielding, no? Then as you remember sa behavior of steel, no? There is this elastic limit or proportional limit, then comes a time nga maabot siya sa ihang yielding strength or point, then mo somewhat horizontal na, if you remember, then na siya pataas, tapos siya strength hangtod maabot ihang ultimate strength, then rupture, no? So for if plastic collapse can be reached, the low deflection curve will have the appearance of either curve 4 or curve 5. So in curve 4 or 5, nakaabot siya sa ihang plastic limit, meaning this 4 and 5 nga representation is mo ni siya tong na-establish og tarong ang beam. So meaning nakaabot siya, ni yield siya, then nakaabot pa siya sa iyang plastic nga limit, then collapse, no? In curve 4 is for the case of uniform moment over the full length of the beam, and curve 5 is for a beam with a variable bending moment gradient. Safe designs can be achieved with beams corresponding to any of these curves but wanted to represent inefficient use of material. Now, as I've said earlier, for 1 and 2 curve, kani siya is inefficient use of material. So, meaning dili mao, no, ang material nga gigamit. So, wala pa lang siya kaabot. Na-fail na siya sa iyang yield point, no? So, dili siya maayo. While kaning 4 and 5, no, are good representation nga kaabot siya sa iyahang ni-yield pa siya, di nakaabot siya sa iyahang plastic nga limit. So, that is for safe designs, no? Because kaning 1 and 2, wala pa gani ni yield, ni collapse na, no? So, hadlock ni siya. But compare aning 4 and 5, ni yield na siya, so meaning that is the your warning signal nga mo carry pa siya load but there mo abot ang time nga mo collapse gid siya. So mo nang good design this for the curve 4 and 5. AISC classification of shapes. AISC classifies cross-sectional shapes, compact, non-compact, or slender depending on the values of the width to thickness ratio. This is you encountered this one in your compression member topic, di ba? For eye shapes, the ratio of the projecting flange and stiffened element is, remember this one, BF divided by 2F, no? So this is the flange, I mean the width, the flange divided by 2 times the thickness, no? And the ratio of the web, which is a stiffened element, H over TW. The classification of shapes is found in section B4 of the specification member properties in table B4.1b. Table 4.1a is for compression members. So it can be summarized as follows, no? You already learned this one, di ba? This lambda is the width to thickness ratio. So lambda sub P is the upper limit of the compact category, and this lambda sub R is the upper limit of the non-compact category. So there is these conditions, no? Then if the width to thickness ratio, no, is less than or equal to the upper limit of the compact category, meaning the flange is continuously connected to the web, the shape is compact, no? Because this is the upper limit. So meaning kung less than siya aning upper limit for compact category, so this width to thickness ratio is the shape is compact. But if the width to thickness ratio, no, is in between the upper limit for the compact category and the upper limit for the non-compact category, so the shape is considered as non-compact. And if kung greater than ang width to thickness ratio to lambda R, no, the shape is slender. So you have to like careful, no, kung slender, non-compact, no, of the shape. The category is based on the worst width to thickness ratio of the cross section. For example, if the web is compact and the flange is non-compact, the shape is classified as non-compact, no? So this means that kung a web is compact and flange is compact, like the overall description of the shape is non-compact siya. So you have to like see this one, no, for member properties, no, table B4.1b. Table 5.3 has been extracted from the AISC table B4.1b and is specialized for hot rolled eye-shaped cross-sections. Table 5.3 also applies to channels, except that the lambda for the flange is BF over TF. Because this is channels, so meaning the lambda na siya is wala na 2 diri, no? PF over TF na lang na siya. But for eye section, your width to thickness ratio is BF over 2F, no? We have this limiting relation, no, for flange and for the web. So this is the width to thickness ratio. Then you have to compare this one with this lambda sub B and lambda sub R. Bending strength of compact shapes. A beam can fail by reaching M sub P, no, the moment the plastic condition and becoming fully plastic, or it can fail by lateral torsional buckling, either elastically or inelastically. It can fail also by flange local buckling, elastically or inelastically, or web local buckling, elastically or inelastically. So meaning the lateral torsional buckling and flange local buckling in web local backlink is it can fail, no, either elastically, no, elastically meaning those region nga the stress is proportional to strain, no, within the before the yielding strength, no, yield point, while inelastically is beyond na siya. So meaning inelastically, this is the plastic condition, no, like after yielding, no, if the maximum bending stress is less than the proportional limit when buckling occurs, the failure is said to be elastic, otherwise it is inelastic. Yes, as I've said, if the maximum bending stress is less than the proportional limit when buckling occurs, meaning ang failure is elastic, then otherwise it is elastic. I already said this one, no, earlier. For convenience, we first categorize beams as compact, non-compact, or slender. The same with we did in the compression members, and then determine the moment resistance based on the degree of lateral support, no. We have two types of beams for this discussion: the hot rolled I shapes bent about the strong axis and loaded in the plane of the weak axis. So we have to first is define now strong axis and weak axis. Now for strong axis for I shapes, no, since beam man siya, so the figure of that I beam is actually nga naman, no, the cross sectional. So nakailo diri sa ibabaw. Then the strong axis ana, no, since you supported, no, I mean you have the loads vertically kani siya, meaning your strong axis is the x-axis and your weak axis here, no, plane of weak axis is the y-axis, no, y-axis imuhang weak axis ana, and the strong axis is your x. Channels bent about the strong axis and either loaded through the shear center or strained against twisting. Two types of beams, no. One is hot rolled I shapes bent about the strong axis and loaded in the plane of weak axis. And channels bent about the strong axis and either loaded through the shear center or restrained against twisting. But emphasis will be on I shapes. Then C shapes are different only in that the width to thickness ratio is may mo siyang BF over TF without 2. Okay, this one for other type of beam, the channels bent about strong axis and either loaded through the shear center or restrained against twisting. So you have C bent about the strong axis. Strong axis ni mo actually is X loaded through shear center. So the shear center, this is for beam, so meaning vertical gyapon siya. We have this one, no, note the shear center is the point on the cross section through which a transverse load must pass if the beam is to bend without twisting. So we have compact shapes. Okay, so we have actually this one is from the table, no, previously kanisha. So you have to check now this lambda sub P and lambda sub R. Now, compact shapes are defined as those whose webs are continuously connected to the flange and that satisfy the following width to thickness ratio requirements for the flange and the web. So you already learned this one for the compact shapes. We have discussed this one in your compression members. Yes, so you have to get this one and then you compare with lambda sub b and lambda sub c, I guess. $2.76. Okay, for the web. No, this is for the web. This is for the flange and this is for the web. The web criterion is met by all standard I and C shapes listed in the manual for FY equals to 56 KSI. Therefore, in most cases, only the flange ratio needs to be checked. Note the built-up welded I shapes can have compact or slender, non-compact or slender webs. Most shapes will also satisfy the flange requirement and will therefore be classified as compact. So most of the time, no, actually the web criterion, no, for this web criterion has met all the standard for I and C shapes listed in the manual. For FY, I think this FY less than or equal to 65 KSI. So therefore, in most cases, only the flange ratio. So kasagaran in most cases, redundant na. In most cases, ang account is, batayan is kaning sa flange section because for the web criterion, actually, nipasar na siya, no? So, kani kasagara ang compute. But most shapes will also classify will also satisfy the flange requirement and will therefore be classified as compact. The non-compact shapes are identified in the dimensions and properties table with the footnote F. Yes, for non-compact shapes. Note that the compression members have different criteria than the flexural members. So a shape could be compact for flexure but shear for compression. Also, shapes with slender compression elements are identified with the footnote C. You have to check this one, no, sa AISC manual kung natuma na ba that you have to see the non-compact shapes and also the footnote C and F. If the beam is compact and has continuous lateral support, or if the embrace length is very short, the nominal moment strength M sub P is a full plastic moment capacity of the shape. So if a beam is compact and has continuous lateral support or the embrace length is very short, so ang tendency magud ni if the beam is compact din napagid siya lateral support din and brace length, no, is short. So maabot jud sa time nga makaabot jud sa atong plastic condition. So meaning this nominal moment will become the moment capacity of the shape. Plastic moment capacity. For members with inadequate lateral support, the moment resistance is limited by the lateral torsion buckling, either inelastic or elastic, no? If the members with adequate lateral support, so possibility is that the moment resistance will be lateral torsion, null buckling strength, either elastic, inelastic, or inelastic. Aside from this failure, no, is are the flange local buckling and the web local buckling. So, ingana, no, ang tendency kung inadequate ang lateral support. So, the moment will only support, no, have resistance by the lateral torsion buckling strength, but either inelastic or elastic. But those two, katong flange buckling and web buckling, it can't be supported by inadequate lateral support. So we have this table, user table, note F1.1, section table for the application of chapter F function. So this section in chapter F, and you have this cross section and flange slenderness and web slenderness. The limit states are the Y. The Y is yielding, no? Yielding and lateral torsion buckling. Kani siya nga. Kind of shape. Napatulog na ako.